Okay, I will continue with the examples on power series. So the tangent inverse of x is c. So we found out that, okay, so first let me back up a little bit. 1 over 1 plus x squared is the sum of minus 1 to the power of n, x to the power of 2n, n from 0 to infinity. This is, if we expand it, it looks like 1 minus x squared plus x cubed, no, x to the fourth, minus x to the sixth plus x to the eighth, minus plus minus for negative 1 less than x less than 1. This was 1 over 1 plus x squared. So if you integrate this, that gives you c plus the integral of this term by term, which gives you minus 1 to the power of n, x to the power of 2n plus 1 over 2n plus 1, n from 0 to infinity. If you want to see it in an expanded form, it's simply c plus, we're going to integrate this. So an integral of 1 is 1x, so you get x, minus x cubed over 3. That's the integral of x squared. Plus x to the fifth over 5. That's the integral of x to the fourth. Minus x to the seventh over 7. And so forth. That's what that is for minus 1 less than x less than 1. So this is in an expanded form, and this is just in the summation form. Okay? So that's what we get. We need to find, so this is tan inverse of x equal to c plus x minus x cubed over 3 plus x to the fifth over 5 minus plus minus for negative 1 less than x less than 1. And we don't know what happens at minus 1 and 1. We're going to test that. But before that, let's figure out what c is. So what we want to do is we want to find the center of expansion of our power series. The center of expansion of our power series is 0. So we stick 0 in for x. So put 0 in for x. And that gives you tan inverse of 0 equals c plus 0 cubed over 3, 0 to the fifth over 5, minus plus minus plus. All of that is 0. And tan inverse of 0 happens to be 0, so c is 0. So that gives us that tan inverse of x is actually 0 plus that summation. So that gives us the sum of negative 1 to the power of n, x to the power of 2n plus 1, divided by 2n plus 1, n from 0 to infinity. So that's the expansion, power series expansion of tan inverse of x. But we have to check what happens at negative 1 and 1. So let's see what happens for x equals 1. For x equals 1, plug 1 in. That gives me negative 1 to the power of n, 1 to the power of 2n plus 1, divided by 2n plus 1. This is the series minus 1 to the power of n, 1 over 2n plus 1, n from 0 to infinity. This is a convergent alternating series. Alternating series test is what you should apply to this, and it's convergent. All right? So it converges at 1. 1 should be included. Let's check negative 1. So if you stick negative 1 in for x, that gives you negative 1 to the n, negative 1 to the power of 2n plus 1, divided by 2n plus 1, n from 0 to infinity. This is negative 1 to the n. So negative 1 to the power of 2n plus 1 happens to be negative 1, because this is always odd. and therefore this is always -1. So that gives you -1 over 2n plus 1, and from 0 to infinity. This is -1 to the power of n plus 1 times 1 over 2n plus 1, and from 0 to infinity. Convergent also, okay? Convergent by alternating series test. So it does converge at 1, it does converge at -1, so it converges for both endpoints. So what we get now is, the final answer is tan inverse of x is 0 for C plus -1 to the power of n, x to the power of 2n plus 1, divided by 2n plus 1, and from 0 to infinity, with the interval of convergence of -1 comma 1. -1 and 1 included. Alright, so we're finished here for this problem. But something interesting, just like we did with the natural log, something interesting is if you stick in 1, that gives you -1 to the power of n divided by 2n plus 1, and from 0 to infinity. This is, if you expand this, that's when n is 0, it gives you 1. When n is 1, it gives you -1 over 3, plus 1 over 5, minus 1 over 7, plus 1 over 9. This converges to tan inverse of 1, which is pi fourth, actually. This is pi fourth. So, what's pi then? It's 4 times of that. So you get 4 minus 4 thirds plus 4 fifths minus 4 sevenths plus 4 ninths. This alternating series converges to pi. So if you want to get an approximate value for pi, add this as far as you can get. And that gives you a good approximation of pi. It's something interesting, okay? Something interesting here. So we know power series, we know a series that converges to pi. All right, let's do a couple more examples, okay? Let me see if I can do the power series for f of x equals 1 over 1 plus x quantity squared. All right, so notice that if I have g of x equals 1 over 1 plus x and differentiate this, this gives me minus 1 over 1 plus x quantity squared. So this is actually almost the derivative of that. It's almost the derivative of that. So we're going to take the derivative of this. Okay, so the function f of x is 1 over 1 plus x squared quantity, 1 over 1 plus x quantity squared. It's the derivative of 1 over 1 plus x, but the negative of it. So let's see, let's start with g of x. That's 1 over 1 plus x. And this is actually minus 1 to the power of n, x to the power of n, and from 0 to infinity, for minus 1 less than x less than 1. So take the derivative, minus 1 over 1 plus x quantity squared. This is minus 1 to the power of n, and x to the power of n minus 1. And from 0 to infinity, you can start from 1, it does not matter. Minus 1 less than x less than 1. So, f of x, which is actually the negative of g prime of x, is the negative of all of that stuff, times n, x to the power of n minus 1, and from 0 to infinity. So push the negative inside, and that increases the power of n here. So that gives you negative 1 to the power of n plus 1 times n times x to the power of n minus 1, and from 0 to infinity. From minus 1 less than x is less than 1. You can check, stick -1 in for x, you're going to get a divergent series. Stick 1 in for x, you're still going to get a divergent series. By differentiating, we cannot increase the interval of convergence. Might possibly decrease it, but not increase. So the power series for 1 over 1 plus x quantity squared is -1, just for cleanliness, just simply. I'm going to put n-1 on both of these, because -1 to n-1 is the same thing as -1 to the power of n, n plus 1. So if you expand this, that will be 0. When n is 1, you get, when n is 1, you get 1 minus 2x plus 3x squared minus 4x cubed. This is the power series expansion of 1 over 1 plus x quantity squared. So the point here is, take the derivative to find something familiar. Not the derivative, I mean the derivative of what's familiar happens to be that one. And hence, take the power series of that familiar expression. Then you may have to make an adjustment for the sign that is produced by taking the derivative. Okay? And the interval of convergence here is -1, 1. All right? Let's do another one. And then I will give you a quiz in this video. So let me do one more example here. Okay? So I have a function f of x equals x cubed over 1 minus 2x quantity squared. So we want to find the power series expansion of this function. And then we'll also find the interval of convergence. Okay? So here's what happens. If you think about it, you take a function g of x, 1 over 1 minus 2x, then you can take the derivative of this. So what's the derivative of this function? The derivative of this function is the derivative of the bottom, the negative of the derivative of the bottom, which is 2, divided by 1 minus 2x quantity squared. So it almost looks like this. There is an x cubed missing. There's too much constants here, the 2. So we're going to make an adjustment to it. But I think I can get this power series first. And then I'm going to divide it by 2 and multiply it by x cubed. It should give me the power series that I want. All right? So 1 over 1 minus 2x is, I think it's 2x to the power of n from 0 to infinity for -1 less than 2x less than 1. We did this in the class before. So this is the same thing as -1/2 less than x less than 1/2. So this is exactly 2 to the power of n, x to the power of n from 0 to infinity. All right, now take the derivative. I'll call this g of x. Take the derivative, 2 over 1 minus 2x quantity squared is, take the derivative of that, that's 2 to the n, x to the power of n minus 1, and from 0 to infinity. Just remember, this is a constant. So it's a constant multiple of x to the power of n. So its derivative is just simply n times x to the minus 1 n times x to n minus 1 times the constant. That's what I just did here. I know this is a little confusing here. That's a constant, and the power here drops down and reduces by 1. That's exactly what we did. We have no x in here, okay? So this is 2 over 1 minus 2x squared. So what is then 1 over 1 minus 2x quantity squared? That's actually 1/2 of this, 2 to the power of n, and x to n minus 1. If you slide the 1/2 in to the summation sign, you're going to get 2 to the power of n minus 1, because 1 less, one of the 2's cancels, times n times x to the power of n minus 1, and from 0 to infinity. And this is true for minus 1/2 less than x less than 1/2. We're going to keep that. So what was the original problem? The original problem was x cubed times of this guy. X cubed times this guy. So what I have to do is just multiply this by x cubed. All right, let's go ahead and do that. So my function f of x, which is x cubed over 1 plus 2x, 1 minus 2x quantity squared, is the sum of 2 to the power of n minus 1 times n times x to the n minus 1 times x cubed, of course, and from 0 to infinity. I just multiplied the whole thing by x cubed. Or let me do this. I'm going to put the x cubed here up front. So I'm going to put x cubed here. But that's not the right way of putting a power series. So I'm going to slide the x cubed in and multiply it with this x to the power of n minus 1. So that will give me 2 to the power of n minus 1 times n times x to the power of n plus 2, and from 0 to infinity. For what x values? The interval of convergence. Because we differentiated, we don't expect to add any more endpoint. Minus 1/2, 1/2. So that is the power series expansion of this function x cubed over 1 minus x 2x quantity squared. So an exercise for you, or a quiz that I would want you to finish, to do, follow this pattern and do and submit, is find the power series expansion of the function x squared over 1 plus 4x quantity squared, and find the interval of convergence of this function. All right, have a nice break and enjoy your Thanksgiving.